So a lot of times we want to be able to calculate the delta H for a given reaction, but there's no direct way of measuring the delta H for that given reaction. Rather, we have to look at different steps that the reaction can take, and then add those steps together along with their delta H values to get the desired equation or reaction that we're solving for. And we can do this because delta H is what we call a state function, which means it's independent of the pathway in which it takes. Meaning, let's say, for example, you take a reaction and it has potential energy diagram like this. The activation energy is always from the activated complex to your reactants. Okay, but let's say you throw in a catalyst. We know catalysts are going to lower the activation energy by lowering the potential energy of your catalyst. So with the catalyst here in red, the quantity of activation energy is lower. Your reaction happens faster. You're providing an alternative pathway for the reaction to take. However, that doesn't change the delta H value, because your delta H is always the difference between your reactants and your products. It's always this value right here. So as you can see in black, the delta H, okay, is the same as the red pathway, because our products and our reactants don't change when we throw in that catalyst. So delta H doesn't matter the pathway or the route in which the reaction takes. All that matters is what you start with and what you end with, and finding that difference between them. So we're applying something called Hess's law, which allows us to add multi-step equations together to get an overall reaction. So for example, in number 1 here, we want to calculate the delta H for this reaction. This is our desired overall equation. We want to solve the delta H for this guy. We don't have that data though, but we know that we have these two equations along with their delta H values, and my goal here is to combine these two equations so that it equals our desired equation. We're going to add up the reactants and products so that they equal our desired equation. So the first thing that I always check for is to make sure I have the correct reactants and the correct products in my desired reaction. So I look here, I have nitrogen on the reactant side as a desired reactant. I look at that first equation, nitrogen is also on the reactant side. That's awesome. I want to leave it that way. I have NO2 as a product, and in my second equation, the NO2 is also on the product side. That's very good. I can't touch that. So what that means is these two given equations are correct in terms of their reactants and their products. Okay, so I don't need to change I don't need to change reactants and products. And then if I add them together, I'll notice that I have 2 NOs on the product side in the first equation, and I also have 2 NOs on the reactant side of the second equation. And I know from net ionic equations, anytime I have one thing on the product side and the same exact thing on the reactant side, they cancel out. And that's exactly what happens. And you notice, if you look at your desired equation, there is no NO, so it should be gone. It needs to cancel out, so that this is very good. And now I just combine anything that's left over. So I have a nitrogen here in the first equation, no other nitrogen, so I just simply write down N2. When I get to the oxygens, I'm going to add their coefficients together because they appear on the same side of the equation. I cannot cancel out the oxygens, but I'm going to add them together because they're on the same side of the arrow. So this is a coefficient of 1, another coefficient of 1, so 1 plus 1 gives me 2. And then my product side, all I have is 2 NO2s left over. So I go back and see, do I have the desired equation that we were solving for? Does this match that? Yes, it does, so we're good. Okay, I had the desired equation. Well, so what is the delta H value? Well, since we just added these two equations together, guess what we had to do to their delta H values? We had to add them together. So I'm going to take the 180 plus the negative 112. And that's going to give me 68 in the units, kilojoules per mole of reaction. Okay, so let's try number 2. I have a desired equation. I would like to take graphite and turn it into diamond. So taking pencil lead, turning it into diamond. That's the desired equation. And I have this information. Okay, so I start the same way. Do I have the correct reactants and the correct products? My reactant, my desired reactant is graphite. So I check the first equation. There's graphite. It's a reactant, so we're good. Okay, leave it. Diamond needs to be on the product side. Well, here's diamond. In this equation, as written, diamond appears on the reactant side. However, in my desired end equation, it has to be on the product side. So guess what? We're going to flip this second equation. We're going to flip it, meaning you're going to turn your reactants into products and your products become your reactants. So we're going to take the CO2. The diamond becomes a product. And the oxygen also a product. So because I just flipped this diamond equation, the delta H value, I'm going to have to change its sign to positive 396. So here's a rule. Anytime I take a reaction or an equation and I switch the reactants in our products, I just change the sign of delta H because, as we just saw earlier, delta H is products minus reactants. So if I'm changing the products and the reactants, I'm going to change the sign. So I'm going to cross out this equation so I don't look at it anymore and confuse myself. Okay? So now I just have these two equations, and let's add them together. Add them. All right, when I add them, I have oxygen on the reactant side here. I have oxygen on the product side there, so they cancel out. Same thing for the CO2s. I have CO2 on the product side up there. It's a reactant down here, so it's gone. So the only thing left is graphite yields diamond. And so now when I calculate the delta H, since I just added two equations together, I also have to add the delta H values. So negative 394 plus 396. That's going to give me 2 kilojoules per mole of reaction. Okay, for number 3, I want you to hit pause real quickly. Try this one, working it out on your own for just a moment, and then hit play again and see how we finish solving this one. Okay, my desired equation is up here. Now I have 3 equations to deal with, but I still go through the same process. I want to make sure I have the correct reactants and the correct products. So H3BO3 needs to be a reactant. Here it is. It is on the reactant side. Okay, we're good there. Let's see. B2O3 needs to be a product. It's a product down here. All right, that's good too. And then I have a bunch of waters. Waters are everywhere. So that doesn't really help me out right now, but I do know that only 3 things can be in my final equation. However, there's some other stuff here that needs to cancel out. This HBO2 needs to go away. Where's that other HBO2? Here it is. I got 4 HBO2s down here. So right now, both of these are on the product side. I know I have to cancel them. So I'm going to have to flip either this first equation or the second one. But I just said that H3BO3, this one has to stay as a reactant. So that means I'm going to need to flip this second equation. So we're going to flip this one. I'm going to rewrite it below. So I get 4 HBO2s, H2B4O7, and a water. Okay, and so since I just flipped it, that means I'm going to change the delta H sign to positive 11.3. And just so I don't confuse myself, I'm going to cross that out and not look at it again. Okay. All right. Anything else that needs to cancel out? Oh, this H2B4O7 needs to cancel out. This guy right here. Okay, well, that's going to work out because I have the same thing here, and they're on opposite sides of the arrow, so they're going to cancel. So it looks like we're good in terms of checking to see if we need to flip our equations. So now when I add them together, we are going to cancel out these guys, H2B4O7s. However, these HBO2s, okay, notice that the coefficient of the first one is a 1. And the coefficient of this one down here is now a 4. Those do not completely cancel out because in order to completely cancel out, you have to have the same coefficient. You have to have the same number of moles. So what I want to do is I want to multiply the first equation by 4. Okay, so I'm going to multiply all the coefficients by 4. And now those 4 HBO2s, now they're going to cancel out with these guys down here. So we're good. But because I just multiplied all those coefficients by 4, I have to multiply this delta H value by 4. Okay, so this becomes negative 0.08. That's my new delta H for reaction number 1. Okay, so now when I go and combine them, these 4 HBO2s, gone. H2B4O7s, gone. And let's just clean this up a bit. What I have left are 4 H3BO3s. Any more reactants? No more reactants. Now for the products, that one's gone. I have 4 waters. And then I have 2 B2O3s. I have another water and another water. Okay, and since I just added those equations together, I need to add the delta H values. So negative 0.08 plus 17.5 plus 11.3. Okay, when I do that, I get 28.72 kilojoules per mole reaction. Okay, so we're looking good. So I go back and I see, do I have the desired equation? We are pretty close. Okay, I can clean this up just a tad. These waters, I can combine them. Those 4 waters plus a water plus another water, that really equals a total of 6 waters. Okay, and if I compare this to the desired equation, I'll notice something. The coefficient of H3BO3 should be 2, but ours says 4. The coefficient of B2O3 should be a 1, ours says 2. And the coefficient of water should be a 3, but ours says 6. So ours is really double what we should have. So to get to that desired equation, we're going to need to divide all these coefficients by 2. Divide by 2, divide by 2, divide by 2. And guess what? We have to do to the delta H. We're going to have to divide that by 2. So now the delta H value is 28.72 divided by 2. I get 14.36 kilojoules per mole of reaction. That's because now our final equation is 2 H3BO3s yields B2O3 solid and 3 H2O liquid. Okay. So there's my final desired equation, and here is my final delta H value.